Okay, off we go. Real quick before we get back into math, as I'm sure everybody knows, there's a pretty serious internet problem out there, and among the casualties, Canvas is not working. So we do not have a attendance quiz today. I don't see any other way around it, so be it. Okay. So last time we were talking about change of variables, and let me rewind a little bit to our sort of general picture. If you find yourself looking at an integral that you need to compute, and if the domain for that integral is something that you find highly undesirable, such as what I tried to draw in this picture right here, here's the move. Here's the way to potentially turn a terribly difficult problem into a reasonably easy problem. Find a way, however you can. We'll talk about different approaches to this. Find a way to view it as being an image of something nicer. Rectangles, of course, are about as nice as you can get. Then the process of doing the pullback, right? Taking, how you have x and y as functions of u and v, plugging in, basically, and turning this expression into an expression in terms of u and v will give you a new integral. The domain for that new integral is this pullback domain that you set up. And you now have, instead of a terrible integral with a terrible domain, you have a new integral with a nice domain, and almost certainly let's not overstate it, but in very many cases, this turns a hard problem into an easy problem. So that's the big picture. Don't forget, when you do this, you've got to insert your stretching factor, right? And what the formula is for that stretching factor, I presented that last time. It's here it is. It's the absolute value of the determinant of the Jacobian, aka the derivative matrix. You got to make sure to remember to stick that in there. And and we did several examples. So we're going to pick up where we left off. First thing I want to do in preparation for this next example is talk about what happens when you take a change of variables function like this, and then you invert it. Right? So instead of, you start off with x and y as functions of u and v, and if you say, you know what, how about this? How about we view u and v as functions of x and y? How will these two stretching factors relate to each other? And it turns out there's a really simple answer to this question, because if I were to take some little region here in the UV plane, and now let's just imagine what would happen if I push that over here into the XY plane. Well, it's going to get stretched out by some sort of a factor, and we know what that factor is. Right? Partial XY, partial UV. We've done that several times. But let's be a little bit more careful about exactly where did we get that from. What we did is we took the partial of the output variables. I didn't think that through very well. Partial of the output variables with respect to the input variables. In general, that's the formula. It's not about left and right, and it's not about their order in the alphabet, obviously, right? It's a question of what's a function of what. So thinking of this function as going to the right, the partial of the outputs with respect to the inputs gives me this expression right here, which again we've seen. So going the other way, when I come back the other way, now all of a sudden u and v are the outputs. Does everybody see that? For this dark blue function going to the left, u and v are the outputs. And we'll take their partials with respect to x and y, which, when we're going to the left here, are the inputs. Right, so partial uv, partial xy is the factor going the other way. So altogether, this region, this little orange region that I have, when you go over and back, first you multiply by the purple factor. Then on the way back, you multiply by this dark blue factor. All together, you get back exactly what you'd started with. So what that tells us, interestingly, is that these two stretching factors, they multiply to 1. Said differently, they are reciprocals of each other. And by the way, this is our second example now of this thing, which is very much not a fraction, actually behaving like a fraction. So yet another justification for why we represent something, writing it as if it's a fraction. Again, because it behaves that way, and it's very handy. Okay, so let's keep that in mind as we do the next example. Seemingly a weird example, and I'll say another word about that in a moment. But we have these 4 curves. Those 4 curves, kind of like this. Those 4 curves bound a region. My picture got a little messy. Anyway, it's this region right here, this orange region. Right, and suppose on that orange region, I want to compute a certain integral. How would I compute that integral? Well, oh my gosh, what a terrible domain. I see a couple of corners that are right in the middle, and if I slice this up the old-fashioned way, I'm going to be doing 3 iterated integrals. Hopefully we can find a clever way around this. All right, so here's the big idea. By the way, this is a very clever idea. I wish I'd thought of it. Somebody showed this to me. That's the reason I know how to do it. Now I'm showing you, and this is going to be why you're going to know how to do it. Don't think to yourself, I never would have thought to that. I never would have thought of that myself. Right? Most of us would not have thought of this ourselves. Okay, so here's the idea. In cases like this, where 2 of the curves are level sets of the same function, and the other 2 curves are level sets of another same function. All right, so that's what we've got here. We've got 2 sets of 2 level sets for each for 2 functions. Here's the move. This is what is going to make this work great. You call the first one U. You call the second one V. And great things are going to happen. You can almost kind of see this coming for some of this. Now, with that highlighted, let me clear a path. Let's think about what happens to this curve right here, xy equals 1. And that path right there, well, wait a second, if u is xy, and if xy is 1, then altogether u is 1. Which means it turns into a straight line. Isn't that clever? Right? I mean, it's one of these things that's, ultimately, connect the dots. U is xy, xy is 1, so u is 1. It's not like it's a deep point, right? But at the same time, it's clever. And altogether, likewise, for the other curves. And in fact, we've got a setup now where we've got a change of variables function that relates this undesirable domain that we started with, and it relates it to this way more desirable, best case scenario, basically, domain being just a rectangle. Yeah.
You can only do it if you have. You can only go from like the image to the going to its image if it has the same number of like sides, right? Because this particular trick working out exactly as I've got it here, correct. But that doesn't mean that it can't also still be nice in some other ways. So like maybe if this one here were xy squared plus xy, okay, well then it would just be, instead of v equals 4, we'd have v plus u equals 4. It would be a little bit different, but it would still be a dramatic improvement probably. So so there's going to be little variations, but the standard, the center of mass, the first example is going to be like this. Is that cool?
Yeah. All right. Okay, so sweet. We're going to turn that integral into this much nicer integral. Now, real quick, I'm going to come down here. We'll go back and finish those calculations in a moment. Reminder, we are looking at this integral. This is what we want to compute on this, again, highly undesirable domain. We are looking to rewrite that as an integral over the much nicer domain, which is a rectangle. That much nicer domain, of course, is in the UV plane. So this new integral that we're trying to form on the right, and we'll get into the insides in a second. But we're trying to take our xy integral that we were given, we're trying to turn it into a UV integral, where we know the domain is awesome. So now let's look at the insides. And I mean, I just kind of writing stuff down here, but that, of course, is that. That means that my differential, my dx dy differential, I need to figure out, apparently, how to rewrite dx dy in terms of du dv. And simple rhetorical question, what is this thing that I would multiply by du dv to get dx dy? Well, again, this is what follows is mathematically nonsense, but it'll always lead you in the right direction. I want that du dv to cancel, so I need partial uv in the denominator. Again, air quotes, cancel. It's not real cancellation, right? But I want those to seemingly sort of cancel so that this xy's in the numerator will sort of track with this xy that I need it to multiply out to be. And so in order to make the pieces fit, in other words, I need for this to be partial xy, partial uv. Does that make sense? Everybody see why I'm motivated? Right? If I want to be able to rewrite this as something kind of like this, I am not interested in partial uv, partial xy. I need partial xy, partial uv. Otherwise, it doesn't work. Okay, so now having identified that we need partial xy, partial uv, let's come back over to here and realize I don't have formulas for x and y in terms of u and v. Right? It's not given. Side note, I'm of course aware that yes, we could solve for x and y. Let's not. The purpose here is to outline a method, right, to see how the process works. Of course, I could have arranged this to be such that it would be algebraically intractable. It would have just made things uglier and for no particular benefit. So we're going to ignore that we actually could have solved for x and y. What I'm going to do is point out that whatever this function is, you have u and v. And so I can, no problem, take the partials of u and v with respect to x and y because I've got them as functions of x and y. So yeah, go ahead, do that part. Right? This is easy, ultimately, taking these partials, assembling as a matrix, etc., and that's that computation. Now, putting it all together, and I realize I have partial uv, partial xy. I want partial xy, partial uv. Thankfully, I know they're reciprocals of each other, right? And so this thing that I need, wrong color. This thing that I need is just going to be the reciprocal of the thing that I have. How we doing? Everybody see what's going on there, right? Now again, there's the details of the computation, but then there's the, why do I need this one, and why is it that one's the only one that I can compute easily, and then bringing them together. Everybody's okay with that? Okay, so I don't want to say it's all over with the shouting, but we're pretty close. It is a matter of just realizing, okay, once you know this, you plug that in, you can multiply these together, and here's what would, at a quick, careless glance, appear to be the integral that's much easier to work out. And then you notice it's a du/dv integral, but the integrand's in terms of x's and y's. And that's the way this is going to work, and it's annoying, right? And we just got through saying, hey, pretend that we can't solve for x and y, right? And sometimes it can be a pain to solve for x and y. So, good news, we still do not have to solve for both x and y. We don't need to solve for x and y individually. I just need to know how to rewrite this integrand in terms of u's and v's. Not x, forget about x, not y, just x to the 7th times y, that one expression is all I have to worry about. Okay. All right. Now, how do you do that? There's a kind of a guess and check kind of procedure here. This is not particularly algorithmic. Every question is going to be a little different, right? So again, let me point to the big picture sort of strategy, and it goes like this. I have, you'll notice, a product of powers of x and y. I'll write these in terms of u and v. Wait a minute. What are u and v? U and v are products of powers of x and y. So if I want to rewrite a product of powers of x and y in terms of products of powers of x and y, here's my theory. Right now, I'm making this up. This is wishful thinking. All right, I'm not about to say something that I have proved. I'm about to say something that seems reasonable. I have a couple of products of powers, and I figure, hey, if I were to take a product of powers of those products of powers, maybe I could produce the particular product of powers that I want. Everybody see why that seems like a reasonable speculation? I mean, what else would I do? What else would I do with this u and v? Would I look to see if maybe I can take a linear combination of u and v to produce that? Doesn't look like it would work, right? But product of powers, I could maybe kind of see how that could work. Okay, so you speculate. Okay, so this is what I have in purple. You guess the form based on the structures that you're looking at. And then you work out the particulars, right? So now I've got to try to figure out how can I solve for A and B. And this is not a particularly sophisticated thing. First I multiply them out. And then I figure, oh my gosh, these expressions look just the same, so apparently I must need A plus B to equal to 7. And I must need A plus 2B to equal to 1. That gives me this. And Math219, and you solve. And that tells you your A and B. And all together then, that integrand that I have, I can rewrite like so. What do you think? Everybody see how that works? All right. Okay, so we've got a couple of victories under our belt. This is a clever trick for how to set up a change of variables. This idea of a rotation, right? Sometimes nice, natural, simple, geometric transformations, rotations, translations, stuff like that. That might be able to do what you need. And sometimes, depending on how the question is stated, sometimes it may be either bluntly given, like in this example, or sometimes you might have to read between the lines, but it might be sort of implied by the way the question is phrased, or whatever. There might be an implied change of variables function. Okay, but what we have not done yet, and reminder, going back to this original page where we first talked about change of variables, I have so far just asserted that the formula for the stretching factor is this, that it's the absolute value of the Jacobian determinant, and I haven't given you any reason to believe that beyond maybe perhaps you trust me, but in terms of mathematical reason, I've given you zero mathematical reason to believe this. Okay. So I'm going to try to give you a little bit of an argument. I think this is reasonable. Keep in mind what we're talking about. We've got some little piece of area over in the UV plane, and we're interested in how much does that area have to get stretched out to produce its image. Little sort of parallelogram-ish thing in the target. All right, so we're trying to figure out by what fraction does that area get stretched out. So roughly speaking, the way we're going to do this, we're just going to realize that the edges of this rectangle are vectors. The edges of this parallelogram are vectors. And furthermore, if I were to look at this vector, that edge, I can think of this vector, easy formula to write down, by the way. I know it's horizontal because this is a nice little pretty rectangle. I know the width is du, so I know the magnitude is du, right? Easy formula. And I know that this represents a displacement in the domain. And if I want to know what is the corresponding displacement in the target, that's what derivative matrices do, right? The derivative matrix takes that input vector and you multiply by the derivative matrix, and that gives you the corresponding output vector, right? That's what derivatives do. Derivatives turn input changes into output changes. Everybody good with that? Likewise for the other edge, of course. And with that noted, it's almost done, frankly. I mean, again, keep in mind, we're trying to figure out what this area is, and in particular, how it relates to the area on the left. That area, of course, is a parallelogram in the plane. We know that that's an absolute value of a determinant. That's how you compute those areas. And now I'm going to leave the linear algebra to y'all. It's a good little exercise. Make sure you're good with your linear algebra. And you rewrite it like this. And lo and behold, we have the output area, dA, written as something times the input area, du dv. And you can see how the linear algebra works out, what is left over, and therefore what is this stretching factor is the absolute value of the Jacobian determinant. So that's where that comes from. What do you think? Broad strokes, big picture. Does everybody see how that goes down? And do check these details. Again, I think this is a good exercise in making sure you remember your linear algebra, that this you can rewrite as this, which you can rewrite as that. All right. Okay. And as always, of course, if in doing this linear algebra, if you get stuck, you're not sure where to go, what to do, come talk to me in office hours. Very happy to help. Right? But I do think it's a good exercise to try to think it through yourself. Yeah, was that
no, I was stretching.
Okay, that's all right. Yeah, no problem, of course. Okay, 3 dimensions. Good news. It's exactly the same ideas. Just now volumes instead of areas. And good news, the stretching factor is again the absolute value of the Jacobian determinant. And again, we have this convenient notation, this fake fraction looking notation. And again, it kind of does what we want it to do, right? There's still this fake fraction. There is a sort of a fake cancellation again that makes it behave kind of like a fraction, makes it seem right. All right, now our motivation on this, why would I want to do such a thing? Well, again, we might have ugly domains, such as, let's say, something like that. And I just want to point out that when you have three-dimensional ugly, that's a whole nother level of ugly. Like, let's think about how to slice this thing up, right? So as I have it drawn, it would appear to have 8 vertices. One's going to be where you start, probably. One's going to be where you end, probably. That means there's 6 vertices in the middle. That means we're talking 7 separate iterated integrals. But it's much worse than that. Because any one of these slices is not a rectangle. Any one of these slices is going to be an ugly 2-dimensional thing with vertices and edges and concerns like that. So each one of those 7 integrals is going to be several. And I would be, if I had to guess, wild guess, something really terrible like this, it could be 20 or 30 separate iterated integrals. And nobody wants to do that. Right? Everybody see why this is a nightmare? Absolute horrifying nightmare. Okay. All right. So if we can turn that into a rectangular box, that's awesome. Okay, now before I get to the next example, there is a little theorem here. This is super easy to check. Everyone should do this. No big deal. All this is saying is that if you look at a linear transformation, in other words, a matrix, right? A matrix acting as a function. The derivative of that linear transformation is the same matrix. It's a little bit weird, a little bit surprising. Here's the way you're going to check this. You're going to check this by writing down a arbitrary matrix, A, B, C, D. Or if you want to go 3-dimensional, A, B, C, D, E, F, G, H, I, whatever. Multiply it out to identify what that linear transformation is in coordinates. Compute the corresponding partial derivatives and assemble into your derivative matrix. And sure enough, you will get that original matrix A back. Right, so this is no big deal. This is a 5-minute exercise, most of which is going to be trying to decide what notation you want to use. And nothing to it. So make sure you can do this. Again, if you get stuck, if you're not sure, come talk to me. Right? Happy to help. Office hours, help room, what have you. Okay, and with that noted, let's take a look at this last example for this section. And this is, again, a very, very hard problem that we're going to turn into an easy problem. Notice we have an integral. Notice that integral is defined on a domain. This domain is a parallelepiped, something like that. Doesn't look that bad. Parallelepipeds they have flat faces and parallel. It seems kind of nice, but again, 8 vertices. One's going to be where you start, one's going to be where you end, probably. And so that means you got 6 vertices in the middle that you're going to slice through, which means you have 7 iterated integrals, except for the fact that those slices are not rectangles. They're either triangles, or parallelograms, or hexagons. And that's it's a eyebrow raiser. It's a good one to think about. And here's how you can persuade yourself some of these will be hexagons. Take a cube, any cube, a dice maybe, right? Hold it by opposing vertices, and then do like this, where you hold it where the one vertex is at the bottom, one vertex is at the top, and then think about what would it look like if you sliced it at the halfway point, and what you'll find is that it will touch 6 of the faces going through. And you just got to get a single die, any cube, of course, will do, and just look at it and persuade yourself, oh my gosh, totally, right? So some of those slices are super annoying. So again, it doesn't look that bad, but this is 20 or 30, I don't know, it depends on the particulars. This is a lot of iterated integrals. Nobody wants to do that. Okay, so here's the move, magic trick. Totally awesome move. The edges that define the parallelepiped. And given, right here they are. Those edges, make those the columns of your matrix, and let that matrix define your linear transformation. That will be your change of variables function. So it's ultimately a simple little trick, right? It's not a lot to remember. We just take those given edge vectors, make those the columns, view that as a function in the usual way. That will be the perfect change of variables function to turn this nightmare into a nice, pretty little cube over there. Now, let me try to persuade you that this does what I claim that it does. And this is ultimately pretty straightforward because we can look at these edges one edge at a time. If I look at E1 here, this first edge, and now let's just think about what's the image of that first edge. Well, when I apply this linear transformation, that E1 edge is going to go where? Where does that go to? Well, it's a linear transformation represented by a matrix. The images of standard basis vectors are the corresponding columns, right? And the corresponding column, first column in this case, is the corresponding edge of this parallelepiped. Everybody see that? So all of the edges, analogous arguments, all the edges of the cube go to all of the edges of the parallelepiped, and we win. Everybody good? Okay. All right. Okay, so again, all we have to do is wave the magic wand and say pull back. And now the integral that we had defined on this deceptively terrible domain pulls back to a new integral that is computed on the unit cube, everyone's favorite domain for a triple integral, 0 to 1, 0 to 1, 0 to 1, world's easiest bounds. And it's all over but the details. Is everybody happy? So for God's sakes, don't try to slice this up, right? That's a road to nowhere, right? Change of variables turns this into an easy problem. Okay. So yeah, and then don't forget your stretching factor, and then you got to rewrite the integrand, a couple little details. Of course, this is the determinant of the derivative matrix, but as we previously noted, the derivative matrix is the matrix itself. Linear transformations are nice like that. And so easy determinant to compute. And yeah. Everybody good? All right, moving along. So yeah, let's talk about coordinate systems again. Y'all remember polar coordinates. Here's polar coordinates. And, you can think of polar coordinates in terms of, oh, well, it's this distance or it's that angle or whatever. And I think it's ultimately easier to think of polar coordinates as a function. Right? It's a function that turns r's and thetas into x's and y's by way of these formulas. And then from that, you can make your inference as to how do I think about r and theta. So there you go. This is how I like to think about polar coordinates. And oh my gosh, check it out. When I have a function from R2 to R2, I could talk about pulling back through this. I could view this as a change of variables function. And it turns out this is like one of the very best change of variables functions out there. It's awesome as a change of variables function. It's like one of the most commonly used change of variables functions. So, ditto, if I can get this thing to cooperate. Here we go. Ditto cylindrical coordinates and spherical coordinates can also be thought of as change of variables functions. And again, very, very useful change of variables functions. Okay, so we're going to see a bunch of examples of using these as change of variables functions. So since we're going to be using these a lot, how about we go ahead and compute the stretching factors once and be done with it? So we don't have to compute those stretching factors every single time, right? Do it once and memorize them. And then you never have to do them again. So well worth your time. Now everyone should do this on their own. Again, at least once in their lives. Again, I've done mine. It's your turn. Do these calculations. They're not that bad. These first two are actually very quick. There's very little going on there. This third one will take you 5 minutes. It's going to look a lot harder than it's going to actually be. Once you write down the matrix and you start writing down the determinant, what you're going to notice is the Pythagorean identity is going to kick in powerfully several times. And after all the fuss and muss of a 3x3 matrix full of trig, it turns out to be this very simple formula, rho squared sine phi. Okay, so again, good exercise. Everyone should do that. By the way, for whatever it's worth, and this is not a threat, this is just an observation. Some years ago, I think it might have been 10 years ago, I had made that an exam question. So I'm just saying, right? I'm not saying I'm going to do it again. But these kinds of things do make really good practice exercises for you all to do, and they also sometimes make good exam questions. So sometimes that overlaps. Okay. Make sure to memorize these. For polar and cylindrical, the Jacobian determinant is R, and for spherical, the Jacobian determinant rho squared sine phi. Okay, now here's the problem. That's not the stretching factor, is it? The stretching factor is the absolute value of that. Nobody likes absolute values, so let's see if we can figure our way around where I don't have to deal with absolute values. And it's a pretty simple move here. What we're going to do to make this absolute value go away is I'm just going to make the choice. I'm going to say, again, I don't have to. I'm choosing to do this of my own free will. I'm going to say, hey, if I were to just promise always to use only non-negative values of R, right? I promise I will not use any negative values of R in doing any of these change of variables. Oh, okay, well now I'm taking an absolute value of something that I already know is positive, or at least non-negative, and the absolute values dissolve. And now our stretching factor is literally just R. No absolute values at all. Is that cool? Everybody on board? So this is a trade-off. I choose to tie my own hands in this way, and the benefit is that I get to avoid the absolute values. But now let's be honest about this for a moment. I don't even like negative values of R. What I'm doing here is I am promising not to do stuff I don't want to do anyway. Right? So this is a very small price to pay. Does that make sense? Likewise with cylindrical coordinates. Just promise to always choose pullback domains where R will always be non-negative. And cool, those absolute values just disappear in a puff of smoke. All right, now the tricky one. A lot of students get this wrong. It's real easy to sort of fall for what I'm going to call a misleading suggestion that spherical coordinates, pretty much polar. It's basically the same as polar. And a lot of students will overinterpret from that and think, oh, okay, well, rho, this rho here, it's pretty much kind of like R, and at least some people write it as R anyway, and so it's probably the same deal. Probably we should just require rho to be non-negative, and again, we can make absolute values go away. But no, I mean, look at the formula here. That wouldn't make a lick of sense, right? If I promise that I will only choose positive values of rho, does that guarantee that these absolute values go away? Not at all. Nonsense. In fact, it doesn't make any difference at all. I was going to get squared anyway. Who cares if rho is positive or negative? Doesn't matter. What matters, we've got to worry about sine phi. And sine phi, if I want to ensure that will be non-negative, then I have to restrict myself on choosing phi to be between 0 and pi. Does that make sense? It's not at all like polar coordinates in that sense. Okay. All right, so these restrictions, very important. You got to keep those in mind, or pay the price and deal with absolute values. And I don't think many students are going to want to pay that price. Okay, so let's do one. Start with a polar example here, and notice we've been asked to compute an integral. Here it is, xy plane integral. My domain is this quarter disk here, the part in the first quadrant, which, by the way, you can do. And if you want to crank this out, again, brute force, do it the old-fashioned way. I mean, feel free. You're not going to like it. You notice that we've got this portion of a circle here. However you slice, you're going to have to either solve for x in terms of y or y in terms of x. One way or the other, you're going to have square roots in your inner bounds, which means you're going to have square roots in your outer integrand, which means you have an ugly integral to do. Right, that outer integral is going to be a stinker. Now, in this case, it's kind of doable. In this case, it's inconvenient, but it is doable. But why would we want to deal with inconvenient but doable when we can make this much easier? Right? Okay. So we're going to use polar coordinates as our change of variables function. And I claim, and this is a convenient observation, that I claim that this rectangle is the pullback domain. We can use this as a pullback domain. In other words, I claim that the image of that red rectangle is this blue quarter disk. Now, how do I know that that's true? Well, let's look at it one edge at a time. Let's think about that edge right there. What can I say about this edge? This edge, r equals 1. And then we start where theta is 0. We end when theta is pi over 2. And what does that translate to over here in the xy plane? Well, it turns into exactly that. Right, so this edge turns into that edge. Everybody see that? And then analogously, this edge turns into that edge, and this edge turns into that edge. Again, you want to think this through, good little details. The weird one is, let's see here, color choices. I guess I'll use orange. This entire left edge, that entire left edge is where r equals 0. So that entire left edge goes down to just the origin. So it's kind of a weird, what the polar coordinates function does here, it's like it sort of smushes it on the left. It's like it pinches this whole left edge down to just a vertex. So anyway, but the punchline is you can see then that this rectangle goes to this quarter disk. Everybody with me? Okay, so we can say pullback. Don't forget your stretching factor. Here it is. There's our stretching factor, R. Right? Which we don't have to recompute. We already computed it. Let me rephrase that. I've already computed it. Y'all are going to compute it, but you will also memorize it, and so we can just cite that is that stretching factor. You also have to plug in, so don't forget X is our cosine theta and Y is our sine theta. Or, more conveniently, you can just recall that x squared plus y squared is r squared. But anyway, that's the plugging in portion. And we've got ourselves our new domain. This new domain, again, the bounds, super convenient. And now integral on a rectangle, nothing to it. And we get to a nice, convenient answer. No square roots. No nasty. What do you think? Everybody all right? All right. Okay, so really nice as a change of variables function. In a lot of circumstances, now I'm going to give you a different take on this. In practice, this is not how most people tend to think about how to use polar coordinates as a change of variables function. There's a streamlined, very convenient, alternative take. And here's the point. If you have some, whatever your domain is here, whatever, and then you have your pullback domain, whatever that is. As you slice over here in the r theta plane, right, here I'm doing theta slices. Right, and that's what you have to do. That you have to slice up your domain, right? That's what I did here. I sliced this up, starting with theta equals 0 and making my way all the way up to theta equals pi over 2. Right? As you're doing those theta slices, notice I know exactly what these look like over here. Each one of these just represents a constant value of theta. And I know what that looks like in the xy plane. Constant values of theta, or something like that. So, said differently, as I am doing my slicing over here on the left, as I'm doing that slicing, I could think of it as, here's my pullback domain, and here's how I'm slicing up the pullback domain. Or I could think of it as, look, here's what those slices look like in the XY world. And you can still totally see, okay, well, there's my first slice. And there's my last slice. All I have to do is remember that, this is where theta is 0, and this, my last slice, this is what theta slices look like. This last slice, that's where theta is pi over 2. And so you draw that same conclusion, you still get the correct bounds. So what's nice is you don't have to redraw your domain, right? So here's the same exact analysis we did in the last example. And notice I've got this all scratched out. You don't even need to draw the pullback. No need to draw the pullback. If you want to know how to slice that, just think about it over here. There's my first slice, theta equals 0, and then keep slicing, etc., etc. And then here's your last slice, theta is pi over 2. And so again, you get the right bounds. We didn't even have to draw the pullback. What do you think? Is everybody buying it? Does it seem reasonable? It's really nice. Now, do make sure to realize, as you're doing this, if you don't draw the change of variables thing, it is, I'm going to confess, it can be easy to sometimes sort of forget that you're doing a change of variables. And if you forget that you're doing a change of variables, there's the risk that you might forget to include your change of variables stretching factor, which of course is critical. You gotta do it. Right? The whole thing is nonsense if you don't include this stretching factor. So you just have to remember that even though we don't draw the pullback and the pullback domain, there is still a change of variables happening, and don't forget that stretching factor. Other than that, this works just fine. Okay, so nice little easy last example here. Let's suppose that our domain is the unit disk. Right? How would I think about this? And I'm gonna as the lingo goes, I'm gonna do it in polar coordinates. By the way, when people say they're going to do the integral in polar coordinates, this is what they're talking about. They're going to do a change of variables where we use the polar coordinates function as our change of. That's all it is. So anyway, we're going to do this in polar coordinates. And as we discussed in the last example, we're going to view this as starting with theta equals 0, which you see right there. And then our thetas will continue to increase. I continue to slice up my domain. I continue to get more and more of the domain, and I'm done only when I get around over to what kind of feels like back to exactly the same direction that I was going, but keep in mind, now I've done a full turnaround. This is no longer theta equals 0. Having done that full turnaround, this is now theta equals 2 pi. So my theta bounds, 0 to 2 pi. Is that cool? And then real quick, looking at a given single slice, and so now asking what's the range of values for R? Well, R starts at the origin, where of course R is 0. We end at that point right there. That's on the curve where R equals 1, and so my upper bound, R equals 1. Don't forget your stretching factor. Plug and chug. Off you go. We'll pick up here next time. Y'all have a good rest of your Monday. See you on Wednesday.